This 1977 Mark 6 cover meter from KoLectric certainly had quite a few surprises for me. It looked classic and in good condition until I delved a little deeper. PCB tracks that had turned to dust, unmarked transistors, dissolved and snapped transistor legs, some nasty dried on chemical. I worked my way through all of those physical problems and then had to work the faults. But I only ever achieved minor incremental improvements. I simply couldn't locate that last problem. This one had me scratching my head, and I couldn't even get the battery test to work. As I grumpily pondered that I'd explored every last avenue, that battery test was niggling me. I stared in my cup of tea and remembered one last thing that I meant to look at. I kept ignoring it. If this failed, it would be scrapped for parts. 10 minutes later, there it was, the culprit, a black hair. So let me take you back to the beginning of this very fraught journey. As you can see, it's in a pretty nice wooden box. I think this wooden box will do up beautifully. It won't need restripping, anything like that. It'll just need some rejuvenating solutions putting on it just to bring back all the life. This is around about a vintage 1977, I reckon. And there we go. There's our equipment. And this is a cover meter Mark 6. And basically its job, we imagine that this is a slab of concrete with a metal bar in the middle to reinforce it, a rebar. So this will measure the distance between the top of the concrete and that bar. It is in millimeters, which is quite interesting. Anyway, this one is complete with its sensing head, and by turning the head on the concrete we can actually determine the direction of the metal bar. Battery powered, so it's a big PP9, and with this being about 1977, then they weren't paying a lot of attention to efficiency of battery powered equipment, hence the huge battery that we've got here. And turn this on, we can see that it moves to a battery test position, and we're nowhere close. We're reading about 20. That's fine. I'm sure I can power this from my DC power supply without any problem at all. Even with the power supply connected, the battery test fails and ranges A and B, which are the measurement ranges, are completely unresponsive. So it's time to take it apart. So inside the box there are some residues, but I don't think the one at the back is glue. It looks pretty nasty to me. We've got a little transformer tucked away in here. Loads of leads just kind of loosely wired across. I mean, you know, there's no reason not to just bring your printed circuit track over here for that one, certainly, because it doesn't even cross anything. There's our power section over here. It seems our power supply comes into there, certainly. Got an electrolytic capacitor there, so that's obviously quite suspect. And then a couple of really old transistors. Some very old style resistors that are also suspect. I mean, obviously this has an oscillator. We've also got a lot of very old trimmers, which look surprisingly clean. I'm going to separate the top from the bottom now. We can have a better look. So obviously we can clean up all this bottom later on, but I don't see why the tracks wouldn't still be properly intact. Although this one here looks like it might not be intact. Okay, so there we have it. Obviously just some switches and pots and things like that on this end. Trimmer there just to give us a better range control. Got a few electrolytics kicking around, which I'll probably replace as a matter of course. A few deposits on the surface. Obviously some corrosion. And if I look at the PCB side, there's a lot of corrosion. In fact, just here in this corner, I would say the corrosion may have removed the copper completely. So yeah, I've got no conduction between those 2 points, and of course it should conduct. So straight away we've got a fault there. We've got another section down here where the track is completely broken. I think most other places, I think I've got the track there. No connectivity between those 2 points, so definitely that track's gone there, definitely the track's gone here. So here and here, that's an easy repair. It would be nice, of course, I think, if I can clean this back thoroughly and just run new solder tinning on all of these tracks. That will help it for a long time. But I think what I'm going to do just for a second is I'm just going to tack a little bit of wire onto these two and just see if that actually brings us back to operations or not. So I'm going to position this one so that it actually follows the track shape. And then at a later point, I'll pop it off, clean down these tracks really thoroughly, and then reattach this fully. It's going to take a lot to get this oxide off here. I'll have to think about what the appropriate cleaner is. And here we go, battery test. Still exactly the same, no more current flow than before. A bit annoying, but kind of hoping that might be a major step forward. Okay, so I'm just running along, testing a load of these old resistors. Yeah, a fair bit of behaviour like that. Well, it's just kind of ramping up, which generally is an indication that we've got a capacitor charging nearby somewhere. They're generally coming out within 10 to 15%, and these are silver coded, so yeah, I'm not expecting super accuracy with anything in here, to be honest. I might need to look further at this back to see whether there's any further places where the tracks have actually broken and I just can't happen to see it at the moment. Let me just test continuity between. Yeah, we've got another continuity break just there. Yeah, no continuity. So okay, I found another break. Let's get that fixed. Right, I'm going to trace through, just see if there are any other breaks that I'm not expecting. Another one there. Nothing. Nothing. I'm pushing in hard with these to make sure I pierce the insulation. Nothing. Wow. This PCB is a disaster. I'm actually wondering now whether I might actually just remake the PCB. But even some of the bits that appear to be connected actually aren't. On that one. So yeah, there's quite a lot of damage on here. Okay, I'm going to try and clean this section down a little bit better. I'm applying here is a very small amount of ferric chloride, which I'm not going to leave on here for very long at all. But hopefully it will dissolve a lot of our oxides fairly quickly. But of course, if I leave it on too long, it'll also dissolve copper traces, so I definitely don't want to do that. Fortunately, I've got this video which tells me where all these traces were if any of them should completely vanish. And like this one just here, because it's only got oxide, it has basically vanished. This will also help me to just solder on these connections as well. Right. So I have wiped that over, only for like 30 seconds or so with some ferric chloride. And we can already see, for example, just here we can see the copper, where the oxides have literally dissolved in just a few seconds. So down here we can see this track has completely vanished. Over here, this one here has vanished. This one here's got a huge break in it. So no wonder we've got a few connectivity problems. The same with this one here. It vanishes pretty quickly to nothing. Could have done with just a few more seconds time with the ferric chloride, I think. I'm just working my way through all the breaks, patching each one with wire, tinning some bits. This might not be the finished repair. For that I probably need to create a new PCB, but I'm not even going to attempt that unless I can get it working first. And I admit I'm quite surprised that that one's connected to anything. So I won't make a decision on whether to make a new board for this until I've found out whether patching everything together, sorting out a few dodgy parts, actually gets it working again, because otherwise what's the point? Okay, so that's it, pretty much bodged together, just a little bit of cleaning to do, and actually I've just spotted a transistor pad on the left hand side that also needs soldering. But once that's done, then I'll be able to give it another test. So I've switched to the top side just to clean off a little bit of residue and things I don't see on the components, and all does not look well. This one here and this one here both have corroded legs. Quite a lot of the component legs are covered in sort of a gunk, so I'm trying to clean them off using this fiberglass brush, and doing so is revealing several transistors with broken legs, or dodgy looking legs in some cases, just badly pitted and corroded, and in some cases broken. Let's see if we can see what parts they are. BC205A. There's no marking on that part, typical. BC208A. So the good news is that these transistors are mainly just general purpose silicon transistors, so easy to replace. Just a 2N3906 or something like that will do for some of them, or 2N3904, and so just bog standard NPN PNP. Now the question is, what about these ones with the missing legs? So I'm having a good old fumble trying to just clip on so that I can actually just measure what this is and also measure its pin out. NPN silicon, HFE225. Okay, so I've found out this is a silicon NPN, it would appear at least, and yeah, HFE of about 250, and not a lot else to write home about, so I just need to find a suitable transistor to drop in its place, and the rest of it I've got part numbers for, so I'll look up equivalents. So I was unable to find good data sheets for the BC205, 206 and 208As, but I did manage to find this page, and this has got the pin out and the basic parameters. So I was able to print this out so I could just use it in the lab. Now the other thing is actually the substitute, and I often use this site, alltransistors.com. We put in what we're interested in, so BC205A in this case. We click transistor equivalent substitute, and it does a search on the parameters. It finds some replacements. Now there's not that many replacements here, and that's because it has a very strange case, a TO106. So we can turn off TO106 and do a search again, and now it finds loads of them. In fact, there's about 1,500. So it's not really going to have huge problems matching that to something in the drawer. And if we look up towards the top, there's a 2N3906. This is a PNP transistor, of course. So most people are going to have a drop in one of those. Now I'm actually going to use, let me see, one of the BC range. Here you go. I'm going to use this BC560B because I've got a bunch of these old stock in the cupboard, and I'm using some 550s for the NPN version as well. One big bonus with these old transistors is the pinout is identical. So I don't have to worry about the pinout. I can just literally drop the transistors in place. So before I replace the transistors and give it another go, I thought it might be quite nice to have a little look at this sensing head and see what technique that they've actually used. So quick look in the top, and all we can really see are two wax discs, but that probably gives it away. And let's take a look at the bottom, and we can see the two coils there. So we know now that our sensor contains two coils orientated as shown in this diagram. So how's it actually doing the sensing? For magnetic sensing like this, I think there are two main methods. So on the right, let's take a look at that one first. So in this we have a single coil in which the coil is forming part of an oscillator circuit. Now as it moves closer and further away from the metal rod, then that metal rod influences the inductance of that coil and changes its behaviour in an oscillator circuit. So we can use that as one method of detecting. The method we're using here though is using two coils, and so I think what's happening here is that we are passing an oscillation into one coil. So it's got an AC magnetic field going all the way around it, and that magnetic field is orientated so it's intersecting fairly precisely, in fact, with whatever metal happens to be underneath it, and this orientation gives it a reasonable amount of range. The changing magnetic flux intersecting the ferrous metal bar is actually causing an electric current to circulate within it. That current circulating in the metal bar, of course, is causing it to create a magnetic field around it that's fluctuating because the current is also fluctuating, and our second coil is able to pick up that fluctuating magnetic flux. That's a mouthful. So that way we're kind of coupling our magnetism through. Take the bar away and the level of coupling reduces. Now there is a problem with this, which of course is that there will be interference, there'll be crosstalk between these two coils even without the bar in place, and so we have to essentially remove that level when we're calculating what to display on the meter. But that's not too big a problem. So anyway, there we go, that's the general principle. So back from the theory, and I'm just working through replacing transistors and any component that looks a bit dodgy. So obviously all the transistors that have broken legs, and then any that look in the least bit dodgy at all. Now I'm taking them out, I'm testing them, they're all actually testing good, but I'm still replacing them if they look a little bit dodgy. I mean, let's face it, why not? Let's be sure that everything is good. Let's see if we're going to have any joy with this then. Okay, well, we've actually got something happening at least. So I've got the meter set to range B, and I'm trying to zero the meter using the coarse and fine adjustments, but they really are all over the shop. As I move this over ferrous objects, we're at least getting some detection happening. However, not nearly enough. So I'm actually at about a distance of about 10 millimeters, maybe 20 millimeters, and it's reading 60. And really it should be pretty much on this end at this point. So yeah, it's getting there. If I just lift this over here, and we can see that that is actually working as a metal detector, but just not very much range. It thinks it's 6 centimeters away, it's about 1 centimeter. So, let's try on range A. It's basically range A zeroed. It reckons it's about 2.5 centimeters away, whereas of course it's only 1 centimeter. Whether we've got some problems with one of these controls up here, and generally quite a mess. Battery test also. So these two parts have been joined up as a variable resistor, which is quite unusual. The one level coarse is 3K. The one level fine is 100 ohms. And they literally are acting as a variable resistor. These do seem to be in quite a state. The question is, should we try and take these apart and clean them? This is actually wire wound. Let's speak to a little bit of whatever it was that was contaminating the main board, but fortunately not too much. So the contact is actually this little rim. It's the top edge of that rim, and I think I can clean that fairly easily. Some IPA here. And so the contact itself should be pretty much cleaning against the roughness of the wire. So this one was performing worse. This is the fine one. But actually it feels to be running smoother, but yeah, it's a bit coarser, this wire wound, but there's a bit of muck on it, but nothing too bad. Anyway, let's try and get it clean. I'm just going to clean on the outside just for a second or two, just so I don't transfer lots of muck all over the place all the time. So I've just spread a bit of deoxidizer into this, for those interested. This stuff, I'm trying to just get down into this centre section as well, where the wipers contact on the centre pin, reduce any noise that might pick up. Might have to spray into that. So just spread my contact cleaner right down into that centre bit there. So we've got this pickup going down here to another contact which wipes on electrical contact for the centre. I want to make sure that wipe is clean as well. I don't know what contaminant this has had in it, but it's had something. I'm not expecting that's particularly fixed anything, but hopefully it will have improved the performance on these two controls a little bit. Alright then, power on. Test, nothing. So the course is behaving a lot better now. It's still failing to find anything at any sort of range, but these adjustments are actually behaving themselves as it's now a very fine adjustment, and it is working. Let's adjust that to basically turn that off. Adjust that to 0. Just there we go. Excellent. That feels to be doing exactly the same as the battery test, which is it's stopping suddenly, but that's at 10. 14 on this scale here. Very similar point. Let's put it on a more sensitive setting. Now if I pick up my spanner, for example, just here, I place it on the workbench, and I bring myself about 8 centimeters above, I'm actually getting an 8 centimeter measurement off that. But the problem comes is, when it gets a bit closer, I'm no longer getting an appropriate measurement. It's as though the meter doesn't want to actually go as far as it should do. So this is starting to prove to be quite annoying. So I've tried to systematically go through the repair. So I've been through the board, looking at all the faults on the board, all the nasty physical damage, and patched all that up. Then I discovered that damage actually extends onto this side of the board, with lots of broken transistor leads and dodgy resistors and things like that. So I've been through all that, replaced those, and although that improved things a lot, still the meter is only going about a third of the way. And I've looked at the oscillator, that's working, and I've tried to look at it systematically, and finally I started looking at the battery test circuit. Now there's nothing to the battery test circuit, it's just, you know, a little bit of loading for the battery and some series resistors and a trimmer for the meter here. And that's still not working. So I have one fearful test left to do. So what I'm beginning to wonder is in fact whether the problem is the actual moving core meter itself. It's a 100 microamp meter. I'm just kind of wondering if that might be my problem. That should be 10 microamps. Okay, so let's disconnect one of these connections from the back of the meter, and we'll connect our 100 microamps through the meter. So I am connected both to the positive and the negative. We'll reverse my polarity. Yeah, okay, there we go. 4, 5, whoa, 6, 7, 8, 9. Well, there's 100 microamps, and that is nowhere near. The actual repair of the board wasn't a waste of time. We've got everything improved quite a lot. Some dodgy transistors with very, very dodgy fragile legs have been replaced. Some with broken legs have been replaced. Iffy other components have been replaced. The board itself has been cleaned and sorted out quite a lot. But this meter right here is not working. So I'm actually going to just connect up another meter in series with that one just to be absolutely certain. 0.1 milliamps, that's 100 microamps. Checking it on the multimeter here, that's 100 microamps and a fraction. And checking it on here, and this should be full scale deflection right now, and it's nothing like. After all that work on the circuit board, the primary problem is actually the meter itself. I don't think I've got another meter of this style, and it's going to be quite expensive to get one, I think. It seems to be actually like it might be physically jamming. It appears on the face of it to be bouncing around quite freely. So I'm just feeling to see if there's a definite obstruction, and I'm not really feeling anything at all. So I don't know if it's going to be visible on the camera or not. Just here. So we've got this red wire here which is feeding in current. Just here is a bit of wire. That should not be there. So what's happening, that piece of wire is coming up, but the piece of wire is coming up and it's hitting this screw, and that is limiting its movement. It is springing around, unfortunately. Alright, let's see, we've taken it out. See what, it's like a cat hair. There we go. Full. So that's not bad. That's full scale deflection. That's 0. Let's turn it flat, which is its operating. Put 100 microamps in it. There you go. How is that? Alright, let's get the lid back on. I don't know if you can see that. Just here. This little fibre was trapped in the mechanism. As the mechanism turned, it's a hair, I think, like a cat hair or something. This fibre was just brushing up against the screw and stopping it moving. Unbelievable. So I've got my power supply set to 9.4 volts. Got battery test turned on. I need to plug the head in. Turn it off. Turn the power on. So 9.5 volts. Test. Bang. Right, so now I actually need to ease that back because it's overreacting. So at 9.5 volts, I'm going to want it pretty much at 100. It's basically saying completely full battery. Let's turn the voltage down. About 7.2 is probably where I would say you would call it a day with your battery. And that's, yeah, that's about 7.2. So we can perhaps just ease it back a little bit further than that, I think. In fact, if I made that read 7.2, that would be pretty good. And if I turn this up to 9.93, we're pretty much reading the voltage of the battery. And that's pretty good. Alright then, let's try it with an actual test. So I think that's about zeroed. Let's grab a lump of metal, like this one. This is kind of a bit like a... So I should be able, in channel A, to read up to 40 millimeters. Well, I reckon that's about 40 millimeters. Well, we can definitely... So my finger's probably about 10-ish. So we're way over the top with that. That's probably about 40. So we're a bit oversensitive. It's moving about 10 centimeters away, and we're not really reading it anymore. Channel B though. Yeah, and channel B is way too sensitive. So we've got to try and trim this off now. The first thing I'm going to do, try and remember which channel is which. So my method is that I'm starting with channel B because channel A seems to be kind of an attenuated version of it. Then I try and adjust the B trimmer so it's possible to get a 0 with the sensor away from the metal, and that's including with the trimming on the top of the unit. But what we want then, of course, is a full deflection if the sensor sits directly on the metal. So 0 and full deflection have to be right, and there's a trimmer for channel B, but if that isn't enough, there's also a trimmer for gain. So playing around with those in kind of an iterative way eventually gets us what we want. That's feeling about right in B. Now if we tune up A, we'll go for that being 4 centimeters. Here's reading 3. It's actually just a bit oversensitive, that's all. I'm reading 5mm and it should be 10. Okay, cool. 10. Great. Seems to be about there. And that is working. May need a bit more calibration in truth, but it certainly gives me an idea. Let's try and B again. And about there. And about 10cm. Just registering. I reckon we're about 5cm there. Not bad. So I'm going to call that about there. One finished repaired unit. Fantastic. Oh, thank goodness. So I'm going to clean out the box and reassemble this now, and just have a little bit of thought as to whether or not to make a new printed circuit board for it. It might be interesting just to see if we've got enough juice left in the battery. Quick battery test. Oh, look at that, yeah, 70%. So we're good to go. We can actually work with that. I'm sure there'll be a little bit more tweaking to be done, but overall seems to be working. So taking a look in here, this edge here, with all this horrible stuff, is the edge where we had trouble. We've also got some problem down there, which is more like rust in truth, but so I think what I'm going to do here is I'm going to clean this. I don't know what's soaked into this seam, but something that's not good for it has found its way in there, and it needs to come out. So I've taken this out in the workshop, and I've used some sharp scrapers to clean all that horribleness off the inside. And what I've done then is I've taken some sealer, so a sanding sealer, which soaks into the grain and any dust or anything that's on there, and essentially seals it in a shellac lacquer. And so I'm going to leave that overnight to dry. It will dry hard and kind of impervious to pretty much anything. So I think that'll do the job and keep everything safe going forward. So tomorrow I intend to do something about trying to rejuvenate this wood. It's a bit scratched, and I'm hoping to get some colour into those scratches just to hide them a little bit, and also to freshen up the surface. All installed, all cleaned up nicely. Working on its battery. There we go. Beautiful. And looking very nice, I have to say. Let's just turn it off for a second and close it up so you can have a look at the finished product. There they go, that's looking pretty nice, and you can see that the finish itself has come up really, really nicely. Nice sheen on there, looks like a new one. So all I've done with this is I've applied a refurbishing solution to it. So I'll put the recipe on the screen, but the simple recipe is you put a very small amount of linseed oil, let's say 1 part linseed oil, and then you want 2 parts of meths and 2 parts of white spirit. But in fact I vary that recipe a little bit, and in place of the meths, so methylated spirits, I tend to use methylated spirits with a coloured shellac dissolved into it. So in this case I actually used button polish, and the reason is that this had quite a lot of scratches through the bare wood, and I actually just wanted to fill them in. So the process is I take this, I give it a wipe over with isopropyl alcohol or something like that to clean it, just to get any gunge off the surface, and then I give it a very, very light sand. So I'm talking about 600 grit, 1000 grit paper, and I'm not removing any finish. I'm literally just dulling the surface and feeling it as I go. And if there's anything stuck on it, I'll feel it then and I can get rid of it, like a bit of glue or something. So it's nice and smooth and very, very dull and horrible looking at that point. Use a tack cloth. So a tack cloth is used in the automotive industry, furniture restoring industry, and it's literally what it says. It's a slightly tacky cloth. Not so tacky it transfers any residue to the wood, but tacky enough that it holds all the dust, because that's what we want to do, get rid of all the dust. Finally, I give it a wipe over with methylated spirits, and the reason for that is it softens the surface of the polish that's already on there. Because what we want to do is we want to blend any sharp edges which are reflecting light that we can see. We want to blend those away, and then a few minutes later I'll just rub it over with the rejuvenating solution. Remember, a tiny little bit of linseed oil, that's actually just a lubricant to help everything move around. A bit of methylated spirits, or methylated spirits with some sort of shellac dissolved into it to give it some colour. And when we say colour, we're hardly talking anything. We're talking kind of a golden colour on the cloth. And a bit of white spirit. And that is going to give you that finish straight off the bat. There's no wax, there's no additional polishing. All I did was rub it in, and you rub it in all directions. You want to rub it right into the grain, into all of the scratches, everything. Give it a final wipe off in the right direction. Leave it for an hour, and that's what you get. Simple as that. So in terms of this clip on the front, which was really badly rusted, all I've done with that is get it on the vise with a hammer and reshape it back to match the other one, and then I've used a brass brush and a bit of polishing compound just to remove all of the rust from it, just so it looks a bit better. Short of sourcing some replacements for it, nothing else was going to happen. But there we go, there it is, one very nice looking instrument. It's a good one. So I hope you enjoyed that. If you did, don't forget to like, subscribe, leave some comments, recommend it to your friends, all that sort of stuff, and I'll see you next time. Bye for now.